About 100 years ago, a theory called quantum theory or quantum physics was developed by physicists to describe what happens in the microscopic world, the world of atoms and molecules. It's a physics which is very different from the classical physics, and the behavior is to be understood very different from what we see on our macroscopic scale. Instead of having a particle who is moving around and you can follow it with your eyes, for example, in the microscopic world, particles are described by wave functions which are simultaneously everywhere. We learned how to use the theories. We also learned what are their consequences for what we see on the macroscopic scale. Stars are formed by atoms and molecules, but in fact the star is of course where you see it in the sky. There were some philosophical questions between Bohr and Einstein about quantum mechanics. What is real? What is really going on with everything? And Einstein at one point asked Bohr, do you think the moon only exists because there's a mouse looking at it? So this thing of the world being there or the world being observed is really something that occupies a lot of physicists. It was also realized, but much, much later, that if it's really true in the microscopic world that particles are in some sense several places at the same time, and we can play with that, we might also build technologies. In fact, there are technologies for sending data which are stored in quantum particles, and since the particles can be multiple valued at the same time, different observables can have different possible outcomes when you look at the system, then you can also hide secrets in these things. That's called quantum cryptography. There are also ideas that we could replace the computer's bits, that is the register value 0 and 1 in all the numbers we deal with when we do a computation, replace those by quantum bits, having physical systems represent the values 0 or 1, but also because they're quantum 0 and 1 at the same time. A lot of this was interesting and fun, but it was not clear where were the real advantages until mid-90s. So around 1994-95, Peter Shaw came up with a theoretical algorithm, so that's a mathematical program to solve a particular problem. The problem that Shaw was interested in was called factoring. If you take two numbers and you multiply them together, that's a fairly easy task. We all learn how to do that in school. But if I tell you this number, 15, is the product of two numbers, then how can you find which two numbers I multiplied? And I guess when I said 15, you thought that's 3 and 5. That's right, because these are small numbers. But if I give you a much bigger number, then you will have to try. Is 2 a factor? Is 3 the factor? What did he actually multiply together to get this big number? And the number of calculations you have to do grow, and they grow fast with the size of the big number. That's in fact very well known, and it's a basis for data security in our classical data processing, that we can hide secrets using the fact that we have this thing being a hard problem. So it was a shock to many when Peter Shaw came about and said, here is a way where we can use the microscopic world, code the data, and perform this task much, much faster for factoring big numbers. Shortly after, another scientist, Love Grower, found a way to look very quickly into databases. And the trick by Love Grower is a different kind of algorithm, which is also using the quantum nature. So with these two ingredients, and of course many more promising things are waiting probably around the corner, physicists have to now go out and see, can we build a machine who can actually do this quantum computing? So we are going to copy in quantum computers the concept of a classical computer. So if you look into a classical computer, it has data stored. It has data stored in the form of bits. So it can typically be a physical property. It can be an electronic component that has a voltage on it, 0 or 1 volt. And when you charge or discharge that device, you switch between 0 and 1. In your memories, it can be a hard disk where there's a magnetized area, it can be magnetized or not, and that is the 0 or the 1. So in the quantum world, we will be looking for physical systems which can also be 0 and 1, but 0 and 1 at the same time. And that is fortunately not the hardest task, because the microscopic systems can be in this several states at the same time. But now they have to be under our control, and that's actually the hard task. Secondly, you're not going to sit with only one bit and doing the calculations. You're going to do what a computer does. It's going to combine different pieces of information. It's going to add numbers, multiply numbers. And this addition and multiplication means that I'm going to take two of these bits, and then I'm going to get a result that depends on both of them. Okay, this is what the transistor does in classical electronics. But if I want to do it in the quantum world, I have to respect the crazy rule, namely that if the first bit is 0 and 1, the second bit is 0 and 1, after the calculation, I still have all possibilities present. And that means I should not go in and lose that state. And one thing that is very special to quantum mechanics, if you look at a quantum system, you tend to project it. You tend to see a classical result, and that kills the quantum state and turns it into a classical bit. So there should be neither me going and looking at the bit in the middle of calculation, but there should also not be a mouse like Einstein's mouse looking at the moon, looking at the quantum computer, because that will also collapse the quantum computer and make it more classical. So how can we do that? And we have to go to the microscopic world, and to do the quantum computations, we have to find particles in the quantum world who interact with each other, because that's the way we are going to make them do something together. And many physicists actually, starting already in the 1990s, came up with ideas. How can my field of physics actually contribute to this research? How can I be the one building the quantum computer with the system I have in my laboratory? And there were already quantum computers in the laboratory. Of course, they had never been used for quantum computing, but there were already people with excitement studying quantum systems who had two different states. And they were already very excited about the way they could flip these systems between these states and also in the superposition of these states. This is what we call the states that are 0 and 1 at the same time. One such community is actually one that many people meet, not because we want to, but if we go to hospital, they can sometimes expose us to what's called a magnetic resonance imaging. And what happens in that process is actually that with radio signals, they excite the nuclear spins in the atoms in our body. And that makes these little spins flip around between the states that we in a computing world would now call 0 and 1 states, and we'll flip them between 0 and 1 in a way so they also populate superposition states. That's a very well-known process. It's been known for decades. It's also been well-known not so much in hospitals, but in chemistry institutes, that if you have a big molecule, there can be many of these atoms, and if you flip one, at the same time look at another atom in the same molecule, it can actually feel the presence of the first one. The atoms are like little magnets, and you all know that if you take one magnet and another magnet, you can actually feel them repel each other or attract each other. And it's exactly the same thing that happens in these molecules. When you drive one molecule, one atom in the molecule, then that will affect the forces and therefore also your ability to rotate the other one. So the magnetic resonance imaging community jumped to the rescue here as a quantum computer, and fair enough, already 6 years later, they could publish the first calculation. And the first calculation was that 15 is equal to 3 times 5. They had actually encoded that in 7 atoms in the same molecule that they had been doing their calculations on. There was immediately excitement, and there was also immediately a criticism, not of the experiment, which was fantastic, but the very idea to build a computer like that. Of course, you also have to have a plan. How do you go to the more than 7? How do you go to the 100? How do you go to the 1,000? If you take your smartphone, there's a chip in that smartphone which is operating with about 1 billion transistors. So how do you build a molecule with 1 billion atoms who can all control each other? And that is actually not possible. So this magnetic resonance idea is really great, but it did not push to the technologies that we see today. Other scientists came in, a little bit more artificial, but still things we did in the lab. So there have been many experiments and famous experiments where people do the same thing with atoms, shining laser light on atoms and making the atoms change their state between a low-lying ground state, as we call it, or a high-lying excited state. All the light that you see around you is typically coming from atoms who are decaying from the excited to the ground state and emit this light. The orange light from the street lamps over the highways is sodium atoms who are emitting such light. And we can also both see the light coming out, but we can also put light on the system and excite it back again. Now you want to build a computer with sodium atoms, good idea. You just have to have single sodium atoms one by one, and then you have to excite them very carefully. And the best way to get atoms one by one is actually to steal one electron off the atom, so it becomes electrically charged, because then you can hold it with electrodes. We call this an ion trap, and the ion trap has electrodes which are large distance away from the ion, so about 1 centimeter or more. In some of the early traps, you had some electrodes, and then there would be this ion floating in the empty space. And when you shine light on that ion, you could make the other electrons in the ion jump up and down, and you could actually do some of these processes. And such research already existed, not motivated by quantum computing, but because such ions could be precise clocks, and scientists are curious. Scientists also wanted to see, can we actually do this, and can we actually play with such ions? And there were great experiments taking place already. But now came a proposal then by smart theorists for doing not only one ion, where you can do the gate operations, that is, do the logic that you want to do in the quantum world, but you could also take two ions and you could make one ion actually influence what happens to the other one. And this happens in the ion trap because they're both charged particles. So they repel each other due to electric forces. And if you push one, the other one can also feel that push because they move with respect to each other. So the ion trap proposal is actually pretty advanced, and you can go on to 3, 4, 5, or even 100 ions if you want to. And then you can have a communication and algorithm for doing calculations with these ions. There's a similar idea with neutral atoms. Neutral atoms are fantastic, and they also have this ability to be excited. The problem with the neutral atoms is, how do you hold them? Because I talked about the electrodes holding the charged atom. The neutral atom is electrically neutral, so you cannot hold it with electrodes. But you can hold it with a laser light, and it's a little bit more complicated. It's a little bit more noisy environment, but people found out actually to make these laser traps also very stable. You can also make two neutral atoms talk to each other. That's again a little bit more complicated because they are neutral, so they don't feel the position as strongly of the other one, but they still feel some attraction from the other atom. That's actually the kind of attraction that's present in Scotch tape sticking to paper. That's the atoms in the tape which is feeling the atoms in the paper by that short range attractive force. So there is a potential to also use that. There's also a more engineered way to actually make the neutral atoms talk, and that is to excite them, the electrons, into very high states, because then the atoms become like a solar system with a big planetary orbit. And that extra contribution to the interaction between two atoms, that there's this light particle moving around at long distance, is also making the interaction much stronger. So that's a proposal which is pursued in many laboratories. And again, we already had atoms in the labs. We already had the trapped atoms in the lab because we liked to use them for spectroscopy. There were also industry projects using them for clocks. So the computer was mostly about designing these operations, designing the interactions the right way, and then also have a protocol to do the calculations. So it's nice to have to our benefit microscopic particles which are already made by nature. They are the atoms and molecules who surround us, and identify that there's already quantum bits hiding inside these systems. In the molecule, the atoms offer atom by atom by atom, and we found this way to actually drive them. We can also trap individual atoms, and then we can also drive them. But there was also a quest to see, can we build technologies that look like the standard technologies for computing? That is, electronic circuits in which we're actually guiding the material in a different way. And this idea has led to research in different directions. One of them is to actually build what's called the superconducting circuit quantum computer. So it's built on electronic circuits that are tiny and have this very particular property that there's no damping of the currents. There's no resistance in these currents, and therefore they can run and stay in quantum states for a long time. You don't want to have the system be damped away to lose the quantum degree of freedom. So therefore people are using superconductors to this task. These are materials where there's no resistance, and actually if you start a current, it will run. And you can actually put them in quantum states, and you can put them at the same time, if you like, in two different quantum states. And the currents are so strong that they are being felt by neighboring components. So this is something that really looks like actually a classical computer. It's technically very complicated, and you would be unpleasantly surprised when I tell you that the temperature at which you operate these devices is about 10 millikelvin. That means 1/100th of a degree from the absolute zero. That's minus 270 degrees. It's very difficult to get to low temperatures. It's also very expensive to have devices going to those low temperatures. But this is the regime in which many of our colleagues are working today, and they're building these devices. The big advantage of this component is that you can print these circuits, and you can print them larger and larger. So in principle, you can imagine that you can go to 2, to 5, to 100 of these bits. And this is a field which is actually dominated by private companies. So IBM has today the biggest of these computers, starting exactly with 5, but now having the latest chip, which has 433 quantum bits, which is really 433 independent units, but who interact with each other in a certain way. This is one of the devices that is built, and you can hold it in your hand until you put it into this very cold fridge. Other devices are operating a slightly different way. Some are more based on semiconductors. Your computer and your smartphone is built on a semiconductor material, and in these materials we can address single atoms, spin degrees of freedom, or we can make what physicists call an artificial atom. So it's a bit like the iron trap. We can trap an atomic iron. We can actually make a trap for a single electron inside a solid state material. So this electron is confined to be in a certain region in space, and we can play games with the electron. So it thinks it's a qubit, and it interacts with electrons around it. So these new quantum computers, sometimes called spin qubits, because we use a degree of freedom called the spin of the electron, is the future for seen by many of our scientist colleagues. So these systems were also studied in the past. Actually, the semiconductor material in your phone or in your laptop computer has been also studied with the purpose of putting impurity atoms into a solid state material of silicon in particular. So again, here there were some benefits from the industry already, and then going to quantum was not impossible, but a difficult step to be overcome. So these things you see in labs around the world, you see ion trap laboratories where they do beautiful experiments with few ions. They demonstrated the gate. You see experiments in laboratories with neutral atoms. They do beautiful things with the excited atoms to do the gates. And you see the superconducting and the spin qubits being explored in laboratories. And then you see industrial partners coming in also. So we will more and more see both an industry which is going to hire, of course, good physicists. They surely already had good physicists on board, but to build their devices. Google has a superconducting quantum computer. IBM has a superconducting quantum computer. Leading Chinese companies are now operating superconducting quantum computers. The atom things are more like spin-out companies. You imagine that you have a scientist. This is a good idea. Let me employ some of my former students and let me go as a director myself into a new company, get some funding, and then see how we can make this professional. It does really not belong in a university laboratory to build a big industrial product as a computer, but you need the manpower for that. So this is why we today see a company like IonQ in America, which is based on one of the leading researchers' research activities, but is now actually a machine you can buy. You can also go to the internet and use it. It's online on the cloud, and therefore you can do calculations on this one. And there are other Quantinuum on the US West Coast, which is also doing the ion trap quantum computer. Neutral atom computers are just now entering the cloud services, and I bet we will soon see the spins as well. A very, very special quantum computer, which is also in the making, is one that uses light particles, photons. It's a wonderful idea to use light particles. They're super cheap. In fact, I'm illuminated here by a huge number of those particles per second. So they're easily accessible. They're very difficult to perturb. They just travel through space and everything is fine. The difficult thing with the photons is actually that they interact so little. They interact not at all with each other. So two light beams can cross each other. It's not like in the Star Wars that they can fight with the swords. In fact, these swords will just pass through each other. But in the quantum world, we need gate operations. We need addition of numbers, for example. And there are different strategies to do that. So one is to actually do measurements on the light. And then if you get certain results, you know the calculation was fine. It's called probabilistic because it does not work every time. And there are other protocols where you use strongly nonlinear materials where the light is interacting inside these materials. And that is very interesting. It's very nice. The problem with strong nonlinear materials is that they are often lossy, so that there's a chance you lose the photons in that process. So it's now the scheme which is not, it's a little bit behind the other schemes, but of course with investments and with a lot of science, they will catch up, or they might actually catch up. And industry is already present also with real venture capital. So this means it's capital where we have not seen any return yet, but the optical computer is also now companies, and you can actually access some of these machines also on the internet.